New Millennium Entertainment presents Stephen W. Hawking's The Theory of Everything.
A Short History of the Universe. Lectures by Stephen Hawking, recorded in Cambridge. First lecture. I am going to give this course of lectures with the help of a computer and a speech synthesizer. You must forgive it the American accent. I have not been able to teach it proper English. I shall try to give an outline of what we think is the history of the universe, from the Big Bang to black holes. In the first lecture I shall briefly review past ideas about the universe, and how we got to our present picture. One might call this the history of the universe. In the second lecture I shall describe how both Newton's and Einstein's theories of gravity led to the conclusion that the universe could not be static. It had to be either expanding or contracting. This in turn implied that there must have been a time, between 10 and 20 billion years ago, when the density of the universe was infinite. This is called the Big Bang. It would have been the beginning of the universe. In the third lecture I shall talk about black holes. These are formed when a massive star, or an even larger body, collapses in on itself, under its own gravitational pull. According to Einstein's general theory of relativity, anyone foolish enough to fall into a black hole will be lost forever. They will not be able to come out of the black hole again. Instead, history, as far as they are concerned, will come to a sticky end at a singularity. However, general relativity is a classical theory, that is, it doesn't take into account the uncertainty principle of quantum mechanics. In the fourth lecture I shall describe how quantum mechanics allows energy to leak out of black holes. Black holes ain't as black as they are painted. In the fifth lecture I shall apply quantum mechanical ideas to the Big Bang and the origin of the universe. This leads to the idea that space-time may be finite in extent, but without boundary or edge. It would be like the surface of the Earth, but with 2 more dimensions. In the sixth lecture, I shall show how this no boundary proposal could explain why the past is so different from the future, even though the laws of physics are time-symmetric. Finally, in the seventh lecture, I shall describe how we are trying to find a unified theory that will include quantum mechanics, gravity, and all the other interactions of physics. If we achieve this, we shall really understand the universe, and our position in it. Ideas about the universe. To come back to the subject of this lecture, the history of ideas about the universe. As long ago as 340 BC, Aristotle, in his book, On the Heavens, was able to put forward 2 good arguments for believing that the Earth was a round ball, rather than a flat plate. First, he realized that eclipses of the moon were caused by the Earth coming between the sun and the moon. The Earth's shadow on the moon was always round, which would be true only if the Earth was spherical. If the Earth had been a flat disk, the shadow would have been elongated and elliptical, unless the eclipse always occurred at a time when the sun was directly above the center of the disk. Second, the Greeks knew from their travels that the pole star appeared lower in the sky when viewed in the south than it did in more northerly regions. From the difference in the apparent position of the pole star in Egypt and Greece, Aristotle even quoted an estimate that the distance around the Earth was 400,000 stadia. It is not known exactly what length a stadium was, but it may have been about 200 yards. This would make Aristotle's estimate about twice the currently accepted figure. The Greeks even had a third argument that the earth must be round, for why else does one first see the sails of a ship coming over the horizon, and only later see the hull? Aristotle thought that the earth was stationary, and that the sun, the moon, the planets, and the stars moved in circular orbits about the earth. He believed this because he felt, for mystical reasons, that the earth was the center of the universe, and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 1st century AD into a complete cosmological model. The earth stood at the center, surrounded by 8 spheres which carried the moon, the sun, the stars, and the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves moved on smaller circles attached to their respective spheres, in order to account for their rather complicated observed paths in the sky. The outermost sphere carried the so-called fixed stars, which always stay in the same positions relative to each other, but which rotate together across the sky. What lay beyond the last sphere was never made very clear, but it certainly was not part of mankind's observable universe. Ptolemy's model provided a reasonably accurate system for predicting the positions of heavenly bodies in the sky. But, in order to predict these positions correctly, Ptolemy had to make an assumption that the moon followed a path which sometimes brought it twice as close to the earth as at other times. And that meant that the moon ought sometimes to appear twice as big as it usually does. Ptolemy was aware of this flaw, but nevertheless his model was generally, although not universally, accepted. It was adopted by the Christian Church as a picture of the universe that was in accordance with Scripture. It had the great advantage that it left lots of room outside the sphere of fixed stars for heaven and hell. A much simpler model, however, was proposed in 1514 by a Polish priest, Nicholas Copernicus. At first, for fear of being accused of heresy, Copernicus published his model anonymously. His idea was that the sun was stationary at the center, and that the earth and the planets moved in circular orbits around the sun. Sadly for Copernicus, nearly a century passed before this idea was to be taken seriously. Then 2 astronomers, the German, Johannes Kepler, and the Italian, Galileo Galilei, started publicly to support the Copernican theory, despite the fact that the orbits it predicted did not quite match the ones observed. The death blow to the Aristotelian Ptolemaic theory came in 1609. In that year, Galileo started observing the night sky with a telescope, which had just been invented. When he looked at the planet Jupiter, Galileo found that it was accompanied by several small satellites or moons, which orbited around it. This implied that everything did not have to orbit directly around the Earth, as Aristotle and Ptolemy had thought. It was, of course, still possible to believe that the Earth was stationary, at the center of the universe. But that the moons of Jupiter moved on extremely complicated paths around the Earth, giving the appearance that they orbited Jupiter. However, Copernicus's theory was much simpler. At the same time, Kepler had modified Copernicus's theory, suggesting that the planets moved not in circles but in ellipses. The predictions now finally matched the observations. As far as Kepler was concerned, elliptical orbits were merely an ad hoc hypothesis, and a rather repugnant one at that, because ellipses were clearly less perfect than circles. Having discovered almost by accident that elliptical orbits fitted the observations well, he could not reconcile them with his idea that the planets were made to orbit the Sun by magnetic forces. An explanation was provided only much later, in 1687, when Newton published his Principia Mathematica Naturalis Causae. This was probably the most important single work ever published in the physical sciences. In it, Newton not only put forward a theory of how bodies move in space and time, but he also developed the mathematics needed to analyze those motions. In addition, Newton postulated a law of universal gravitation. This said that each body in the universe was attracted towards every other body by a force, which was stronger the more massive the bodies, and the closer they were to each other. It was the same force which caused objects to fall to the ground. The story that Newton was hit on the head by an apple is almost certainly apocryphal. All Newton himself ever said was that the idea of gravity came to him as he sat in a contemplative mood, and was occasioned by the fall of an apple. Newton went on to show that, according to his law, gravity causes the moon to move in an elliptical orbit around the Earth, and causes the Earth and the planets to follow elliptical paths around the Sun. The Copernican model got rid of Ptolemy's celestial spheres, and with them, the idea that the universe had a natural boundary. The fixed stars did not appear to change their relative positions as the Earth went round the Sun. It therefore became natural to suppose that the fixed stars were objects, like our Sun, but much farther away. This raised a problem. Newton realized that, according to his theory of gravity, the stars should attract each other, so it seemed they could not remain essentially motionless. Would they not all fall together at some point? In a letter in 1691 to Richard Bentley, another leading thinker of his day, Newton argued that this would indeed happen if there were only a finite number of stars. But he reasoned that if, on the other hand, there were an infinite number of stars, distributed more or less uniformly over infinite space, this would not happen, because there would not be any central point for them to fall to. This argument is an instance of the pitfalls that one can encounter when one talks about infinity. In an infinite universe, every point can be regarded as the center, because every point has an infinite number of stars on each side of it. The correct approach, it was realized only much later, is to consider the finite situation, in which the stars all fall in on each other. One then asks how things change if one adds more stars roughly uniformly distributed outside this region. According to Newton's law, the extra stars would make no difference at all to the original ones, and so the stars would fall in just as fast. We can add as many stars as we like, but they will still always collapse in on themselves. We now know it is impossible to have an infinite static model of the universe, in which gravity is always attractive. It is an interesting reflection on the general climate of thought before the 20th century, that no one had suggested that the universe was expanding or contracting. It was generally accepted that either the universe had existed forever in an unchanging state, or that it had been created at a finite time in the past, more or less as we observe it today. In part this may have been due to people's tendency to believe in eternal truths, as well as the comfort they found in the thought that even though they may grow old and die, the universe is unchanging. Even those who realized that Newton's theory of gravity showed that the universe could not be static, did not think to suggest that it might be expanding. Instead, they attempted to modify the theory by making the gravitational force repulsive at very large distances. This did not significantly affect their predictions of the motions of the planets, but it would allow an infinite distribution of stars to remain in equilibrium, with the attractive forces between nearby stars being balanced by the repulsive forces from those that were farther away. However, we now believe such an equilibrium would be unstable. If the stars in some region got only slightly near each other, the attractive forces between them would become stronger and would dominate over the repulsive forces. This would mean that the stars would continue to fall towards each other. On the other hand, if the stars got a bit further away from each other, the repulsive forces would dominate and drive them further apart. Another objection to an infinite static universe is normally ascribed to the German philosopher Heinrich Albers. In fact, various contemporaries of Newton had raised the problem, and the Albers article of 1823 was not even the first to contain plausible arguments on this subject. It was, however, the first to be widely noted. The difficulty is that in an infinite static universe, nearly every line of sight would end on the surface of a star. Thus one would expect that the whole sky would be as bright as the sun, even at night. Albers' counter-argument was that the light from distant stars would be dimmed by absorption by intervening matter. However, if that happened, the intervening matter would eventually heat up until it glowed as brightly as the stars. The only way of avoiding the conclusion that the whole of the night sky should be as bright as the surface of the sun would be if the stars had not been shining forever, but had turned on at some finite time in the past. In that case, the absorbing matter might not have heated up yet, or the light from distant stars might not yet have reached us. And that brings us to the question of what could have caused the stars to have turned on in the first place. The beginning of the universe. The beginning of the universe had, of course, been discussed for a long time. According to a number of early cosmologies, and the Jewish Christian Muslim tradition, the universe started at a finite, and not very distant, time in the past. One argument for such a beginning was the feeling that it was necessary to have a first cause to explain the existence of the universe. Another argument was put forward by St. Augustine in his book, The City of God. He pointed out that civilization is progressing, and we remember who performed this deed, or developed that technique. Thus man, and so also perhaps the universe, could not have been around all that long. For otherwise, we would have already progressed more than we have. St. Augustine accepted a date of about 5000 BC for the creation of the universe according to the book of Genesis. It is interesting that this is not so far from the end of the last ice age, about 10,000 BC, which is when civilization really began. Aristotle, and most of the other Greek philosophers, on the other hand, did not like the idea of a creation, because it smacked too much of divine intervention. They believed, therefore, that the human race, and the world around it, had existed, and would exist, forever. They had already considered the argument about progress, described earlier, and answered it by saying that there had been periodic floods or other disasters, which repeatedly set the human race right back to the beginning of civilization. When most people believed in an essentially static and unchanging universe, the question of whether or not it had a beginning was really one of metaphysics or theology. One could account for what was observed either way. Either the universe had existed forever, or, It was set in motion at some finite time, in such a manner as to look as though it had existed forever. But in 1929, Edwin Hubble made the landmark observation that wherever you look, distant stars are moving rapidly away from us. In other words, the universe is expanding. This means that at earlier times objects would have been closer together. In fact, it seemed that there was a time, about 10 or 20,000 million years ago, when they were all at exactly the same place. This discovery finally brought the question of the beginning of the universe into the realm of science. Hubble's observations suggested that there was a time, called the Big Bang, when the universe was infinitesimally small, and therefore infinitely dense. If there were events earlier than this time, then they could not affect what happens at the present time. Their existence can be ignored because it would have no observational consequences. One may say that time had a beginning at the Big Bang, in the sense that earlier times simply would not be defined. It should be emphasized that this beginning in time is very different from those that had been considered previously. In an unchanging universe, a beginning in time is something that has to be imposed by some being outside the universe. There is no physical necessity for a beginning. One can imagine that God created the universe at literally any time in the past. On the other hand, if the universe is expanding, there may be physical reasons why there had to be a beginning. One could still believe that God created the universe at the instant of the Big Bang. He could even have created it at a later time, in just such a way as to make it look as though there had been a Big Bang. But it would be meaningless to suppose that it was created before the Big Bang. An expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job. Second lecture. The Expanding Universe. Our Sun and the nearby stars are all part of a vast collection of stars called the Milky Way galaxy. For a long time, it was thought that this was the whole universe. It was only in 1924 that the American astronomer Edwin Hubble demonstrated that ours was not the only galaxy. There were in fact many others, with vast tracts of empty space between them. In order to prove this, he needed to determine the distances to these other galaxies. We can determine the distance of nearby stars by observing how they change position as the Earth goes round the Sun. But other galaxies are so far away that, unlike nearby stars, they really do appear fixed. Hubble was forced, therefore, to use indirect methods to measure the distances. Now the apparent brightness of a star depends on two factors, its luminosity and how far it is from us. For nearby stars, we can measure both their apparent brightness and their distance, so we can work out their luminosity. Conversely, if we knew the luminosity of stars in other galaxies, we could work out their distance by measuring their apparent brightness. Hubble argued that there were certain types of stars which always had the same luminosity when they were near enough for us to measure. If therefore we found such stars in another galaxy, we could assume that they had the same luminosity. Thus, we could calculate the distance to that galaxy. If we could do this for a number of stars in the same galaxy, and our calculations always gave the same distance, we could be fairly confident of our estimate. In this way, Edwin Hubble worked out the distances to 9 different galaxies. We now know that our galaxy is only one of some 100,000 million that can be seen using modern telescopes, each galaxy itself containing some 100,000 million stars. We live in a galaxy that is about 100,000 light years across and is slowly rotating. The stars in its spiral arms orbit around its center about once every 100 million years. Our sun is just an ordinary, average-sized, yellow star near the outer edge of one of the spiral arms. We have certainly come a long way since Aristotle and Ptolemy, when we thought that the Earth was the center of the universe. Stars are so far away that they appear to us to be just pinpoints of light. We cannot determine their size or shape. So how can we tell different types of star apart? For the vast majority of stars, there is only one characteristic feature that we can observe: the color of their light. Newton discovered that if light from the sun passes through a prism, it breaks up into its component colors, its spectrum, like in a rainbow. By focusing a telescope on an individual star or galaxy, one can similarly observe the spectrum of the light from that star or galaxy. Different stars have different spectra, but the relative brightness of the different colors is always exactly what one would expect to find in the light emitted by an object that is glowing red hot. This means that we can tell a star's temperature from the spectrum of its light. Moreover, we find that certain very specific colors are missing from star spectra, and these missing colors may vary from star to star. We know that each chemical element absorbs a characteristic set of very specific colors. Thus, by matching these to those which are missing from a star spectrum, we can determine exactly which elements are present in the star's atmosphere. In the 1920s, when astronomers began to look at the spectra of stars in other galaxies, they found something most peculiar. There were the same characteristic sets of missing colors as for stars in our own galaxy, but they were all shifted by the same relative amount towards the red end of the spectrum. The only reasonable explanation of this was that the galaxies were moving away from us, and the frequency of the light waves from them was being reduced, or redshifted, by the Doppler effect. Listen to a car passing on the road. As the car is approaching, its engine sounds at a higher pitch, corresponding to a higher frequency of sound waves, and when it passes and goes away, it sounds at a lower pitch. The behavior of light or radio waves is similar. Indeed, the police make use of the Doppler effect to measure the speed of cars by measuring the frequency of pulses of radio waves reflected off them. In the years following his proof of the existence of other galaxies, Hubble spent his time cataloging their distances and observing their spectra. At that time, most people expected the galaxies to be moving around quite randomly, and so expected to find as many spectra which were blue-shifted as ones which were red-shifted. It was quite a surprise, therefore, to find that the galaxies all appeared red-shifted. Every single one was moving away from us. More surprising still was the result which Hubble published in 1929. Even the size of a galaxy's redshift was not random, but was directly proportional to the galaxy's distance from us. Or, in other words, the farther a galaxy was, the faster it was moving away. And that meant that the universe could not be static, as everyone previously thought, but was in fact expanding, The distance between the different galaxies was growing all the time. The discovery that the universe was expanding was one of the great intellectual revolutions of the 20th century. With hindsight, it is easy to wonder why no one had thought of it before. Newton and others should have realized that a static universe would soon start to contract under the influence of gravity. But suppose that instead of being static, the universe was expanding. If it was expanding fairly slowly, the force of gravity would cause it eventually to stop expanding and then to start contracting. However, if it was expanding at more than a certain critical rate, gravity would never be strong enough to stop it, and the universe would continue to expand forever. This is a bit like what happens when one fires a rocket upwards from the surface of the Earth. If it has a fairly low speed, gravity will eventually stop the rocket, and it will start falling back. On the other hand, if the rocket has more than a certain critical speed, about 7 miles a second, gravity will not be strong enough to pull it back, so it will keep going away from the Earth forever. This behavior of the universe could have been predicted from Newton's theory of gravity at any time in the 19th, the 18th or even the late 17th centuries. Yet so strong was the belief in a static universe that it persisted into the early 20th century. Even when Einstein formulated the general theory of relativity in 1915, he was sure that the universe had to be static. He therefore modified his theory to make this possible, introducing a so-called cosmological constant into his equations. This was a new anti-gravity force which, unlike other forces, did not come from any particular source, but was built into the very fabric of spacetime. His cosmological constant gave spacetime an inbuilt tendency to expand, and this could be made to exactly balance the attraction of all the matter in the universe, so that a static universe would result. Only one man, it seems, was willing to take general relativity at face value. While Einstein and other physicists were looking for ways of avoiding general relativity's prediction of a non-static universe, the Russian physicist, Alexander Friedmann, instead set about explaining it. The Friedmann models. The equations of general relativity, which determine how the universe evolves in time, are too complicated to solve in detail. So what Friedmann did instead was to make two very simple assumptions about the universe: that the universe looks identical in whichever direction we look, and that this would also be true if we were observing the universe from anywhere else. On the basis of general relativity and these two assumptions, Friedmann showed that we should not expect the universe to be static. In fact, in 1922, several years before Edwin Hubble's discovery, Friedmann predicted exactly what Hubble found. The assumption that the universe looks the same in every direction is clearly not true in reality. For example, the other stars in our galaxy form a distinct band of light across the night sky, called the Milky Way. But if we look at distant galaxies, there seem to be more or less the same number of them in each direction. So the universe does seem to be roughly the same in every direction, provided one views it on a scale large compared to the distance between galaxies. For a long time, this was sufficient justification for Friedman's assumption, as a rough approximation to the real universe. But more recently, a lucky accident uncovered the fact that Friedman's assumption is in fact a remarkably accurate description of our universe. In 1965, two American physicists, Arno Penzias and Robert Wilson, were working at the Bell Labs in New Jersey on the design of a very sensitive microwave detector for communicating with orbiting satellites. They were worried when they found that their detector was picking up more noise than it ought to, and that the noise did not appear to be coming from any particular direction. First they looked for bird droppings on their detector, and checked for other possible malfunctions, but soon ruled these out. They knew that any noise from within the atmosphere would be stronger when the detector is not pointing straight up than when it is, because the atmosphere appears thicker when looking at an angle to the vertical. The extra noise was the same whichever direction the detector pointed, so it must come from outside the atmosphere. It was also the same day and night, and throughout the year, even though the Earth was rotating on its axis and orbiting around the Sun. This showed that the radiation must come from beyond the solar system, and even from beyond the galaxy, as otherwise it would vary, as the Earth pointed the detector in different directions. In fact, we know that the radiation must have traveled to us across most of the observable universe. Since it appears to be the same in different directions, the universe must also be the same in every direction, at least on a large scale. We now know that whichever direction we look in, this noise never varies by more than 1 part in 10,000. So Penzias and Wilson had unwittingly stumbled across a remarkably accurate confirmation of Friedman's first assumption. At roughly the same time, two American physicists at nearby Princeton University, Bob Dickey and Jim Peebles, were also taking an interest in microwaves. They were working on a suggestion made by George Gamow, once a student of Alexander Friedman, that the early universe should have been very hot and dense, glowing white hot. Dickey and Peebles argued that we should still be able to see this glowing, because light from very distant parts of the early universe would only just be reaching us now. However, the expansion of the universe meant that this light should be so greatly redshifted that it would appear to us now as microwave radiation. Dickey and Peebles were looking for this radiation when Penzias and Wilson heard about their work and realized that they had already found it. For this, Penzias and Wilson were awarded the Nobel Prize in 1978, which seems a bit hard on Dickey and Peebles. Now at first sight, all this evidence that the universe looks the same whichever direction we look in might seem to suggest there is something special about our place in the universe. In particular, it might seem that if we observe all other galaxies to be moving away from us, then we must be at the center of the universe. There is, however, an alternative explanation. The universe might also look the same in every direction as seen from any other galaxy. This, as we have seen, was Friedman's second assumption. We have no scientific evidence for, or against, this assumption. We believe it only on grounds of modesty. It would be most remarkable if the universe looked the same in every direction around us, but not around other points in the universe. In Friedman's model, all the galaxies are moving directly away from each other. The situation is rather like steadily blowing up a balloon, which has a number of spots painted on it. As the balloon expands, the distance between any two spots increases, but there is no spot which can be said to be the center of the expansion. Moreover, the farther apart the spots are, the faster they will be moving apart. Similarly, in Friedman's model, the speed at which any two galaxies are moving apart is proportional to the distance between them. So it predicted that the redshift of a galaxy should be directly proportional to its distance from us, exactly as Hubble found. Despite the success of his model and his prediction of Hubble's observations, Friedman's work remained largely unknown in the West. It became known only after similar models were discovered in 1935 by the American physicist Howard Robertson and the British mathematician Arthur Walker, in response to Hubble's discovery of the uniform expansion of the universe. Although Friedman found only one, there are in fact three different kinds of model which obey Friedman's two fundamental assumptions. In the first kind, which Friedman found, the universe is expanding sufficiently slowly that the gravitational attraction between the different galaxies causes the expansion to slow down and eventually to stop. The galaxies then start to move towards each other, and the universe contracts. The distance between two neighboring galaxies starts at 0, increases to a maximum, and then decreases back down to 0 again. In the second kind of solution, the universe is expanding so rapidly that the gravitational attraction can never stop it, though it does slow it down a bit. The separation between neighboring galaxies in this model starts at 0, and eventually the galaxies are moving apart at a steady speed. Finally, there is a third kind of solution, in which the universe is expanding only just fast enough to avoid recollapse. In this case, the separation also starts at 0 and increases forever. However, the speed at which the galaxies are moving apart gets smaller and smaller, although it never quite reaches 0. A remarkable feature of the first kind of Friedman model is that in it the universe is not infinite in space, but neither does space have any boundary. Gravity is so strong that space is bent round onto itself, making it rather like the surface of the Earth. If one keeps traveling in a certain direction on the surface of the Earth, one never comes up against an impassable barrier or falls over the edge, but eventually comes back to where one started. Space, in the first Friedman model, is just like this, but with 3 dimensions, instead of 2 for the Earth's surface. The fourth dimension, time, is also finite in extent, but it is like a line with 2 ends or boundaries, a beginning and an end. We shall see later that when one combines general relativity with the uncertainty principle of quantum mechanics, it is possible for both space and time to be finite, without any edges or boundaries. The idea that one could go right round the universe and end up where one started makes good science fiction, but it doesn't have much practical significance, because it can be shown that the universe would recollapse to 0 size before one could get round. You would need to travel faster than light in order to end up where you started, before the universe came to an end, and that is not allowed. But which Friedman model describes our universe? Will the universe eventually stop expanding and start contracting, or will it expand forever? To answer this question, we need to know the present rate of expansion of the universe, and its present average density. If the density is less than a certain critical value, determined by the rate of expansion, the gravitational attraction will be too weak to halt the expansion. If the density is greater than the critical value, gravity will stop the expansion at some time in the future and cause the universe to recollapse. We can determine the present rate of expansion by measuring the velocities at which other galaxies are moving away from us, using the Doppler effect. This can be done very accurately. However, the distances to the galaxies are not very well known, because we can only measure them indirectly. So all we know is that the universe is expanding by between 5% and 10% every 1,000 million years. However, our uncertainty about the present average density of the universe is even greater. If we add up the masses of all the stars that we can see in our galaxy and other galaxies, the total is less than 1/100th of the amount required to halt the expansion of the universe, even on the lowest estimate of the rate of expansion. But we know that our galaxy and other galaxies must contain a large amount of dark matter, which we cannot see directly, but which we know must be there, because of the influence of its gravitational attraction on the orbits of stars and gas in the galaxies. Moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters, by its effect on the motion of the galaxies. When we add up all this dark matter, we still get only about 1/10th of the amount required to halt the expansion. However, there might be some other form of matter, which we have not yet detected, and which might still raise the average density of the universe up to the critical value needed to halt the expansion. The present evidence therefore suggests that the universe will probably expand forever. But don't bank on it. All we can really be sure of is that even if the universe is going to recollapse, it won't do so for at least another 10,000 million years, since it has already been expanding for at least that long. This should not unduly worry us, since by that time, unless we have colonies beyond the solar system, mankind will long since have died out, extinguished along with the death of our sun. The Big Bang. All of the Friedmann solutions have the feature that at some time in the past, between 10 and 20,000 million years ago, the distance between neighboring galaxies must have been zero. At that time, which we call the Big Bang, the density of the universe and the curvature of spacetime would have been infinite. This means that the general theory of relativity, on which Friedmann's solutions are based, predicts that there is a singular point in the universe. All our theories of science are formulated on the assumption that spacetime is smooth and nearly flat, so they would all break down at the Big Bang singularity, where the curvature of spacetime is infinite. This means that even if there were events before the Big Bang, one could not use them to determine what would happen afterwards, because predictability would break down at the Big Bang. Correspondingly, if we know only what has happened since the Big Bang, we could not determine what happened beforehand. As far as we are concerned, events before the Big Bang can have no consequences, so they should not form part of a scientific model of the universe. We should therefore cut them out of the model, and say that time had a beginning at the Big Bang. Many people do not like the idea that time has a beginning, probably because it smacks of divine intervention. The Catholic Church, on the other hand, had seized on the Big Bang model, and in 1951 officially pronounced it to be in accordance with the Bible. There were a number of attempts to avoid the conclusion that there had been a Big Bang. The proposal which gained widest support was called the steady-state theory. It was suggested in 1948 by two refugees from Nazi-occupied Austria, Hermann Bondi and Thomas Gold, together with a Briton, Fred Hoyle, who had worked with them on the development of radar during the war. The idea was that as the galaxies moved away from each other, new galaxies were continually forming in the gaps in between, from new matter that was being continually created. The universe would therefore look roughly the same, at all times as well as at all points of space. The steady-state theory required a modification of general relativity to allow for the continual creation of matter, but the rate that was involved was so low, about 1 particle per cubic kilometer per year, that it was not in conflict with experiment. The theory was a good scientific theory, in the sense that it was simple, and it made definite predictions which could be tested by observation. One of these predictions was that the number of galaxies, or similar objects, in any given volume of space, should be the same wherever, and whenever, we look in the universe. In the late 1950s and early 1960s, a survey of sources of radio waves from outer space was carried out at Cambridge by a group of astronomers, led by Martin Ryle. The Cambridge group showed that most of these radio sources must lie outside our galaxy, and also that there were many more weak sources than strong ones. They interpreted the weak sources as being the more distant ones, and the stronger ones as being near. Then there appeared to be fewer sources per unit volume of space for the nearby sources than for the distant ones. This could have meant that we were at the center of a great region in the universe, in which the sources were fewer than elsewhere. Alternatively, it could mean that the sources were more numerous in the past, at the time that the radio waves left on their journey to us, than they are now. Either explanation contradicted the predictions of the steady-state theory. Moreover, the discovery of the microwave radiation by Penzias and Wilson in 1965 also indicated that the universe must have been much denser in the past. The steady-state theory therefore had regretfully to be abandoned. Another attempt to avoid the conclusion that there must have been a Big Bang, and therefore a beginning of time, was made by two Russian scientists, Evgeny Lifshitz and Isaac Kalatnikov, in 1963. They suggested that the Big Bang might be a peculiarity of Friedmann's models alone, which after all, were only approximations to the real universe. Perhaps, of all the models which were roughly like the real universe, only Friedmann's would contain a Big Bang singularity. In Friedmann's models, the galaxies are all moving directly away from each other. So it is not surprising that at some time in the past, they were all at the same place. In the real universe, however, the galaxies are not just moving directly away from each other, they also have small sideways velocities. So, in reality, they need never have been all at exactly the same place, only very close together. Perhaps then the current expanding universe resulted not from a Big Bang singularity, but from an earlier contracting phase. As the universe had collapsed, the particles in it might not have all collided, but they might have flown past, and then away from each other, producing the present expansion of the universe. How then could we tell whether the real universe should have started out with a Big Bang? What Lifshitz and Kalatnikov did was to study models of the universe which were roughly like Friedmann's models, but which took account of the irregularities, and random velocities of galaxies in the real universe. They showed that such models could start with a Big Bang, even though the galaxies were no longer always moving directly away from each other. But they claimed that this was still only possible in certain exceptional models, in which the galaxies were all moving in just the right way. They argued that, since there seemed to be infinitely more Friedman-like models, without a Big Bang singularity, than there were with one, we should conclude that it was very unlikely that there had been a Big Bang. They later realized, however, that there was a much more general class of Friedman-like models, which did have singularities, and in which the galaxies did not have to be moving any special way. They therefore withdrew their claim in 1970. The work of Lifshitz and Koladnikov was valuable, because it showed that the universe could have had a singularity, a Big Bang, if the general theory of relativity was correct. However, it did not resolve the crucial question, does general relativity predict that our universe should have a Big Bang, a beginning of time? The answer to this came out of a completely different approach, started by a British physicist, Roger Penrose, in 1965. He used the way light cones behave in general relativity, and the fact that gravity is always attractive, to show that a star which collapses under its own gravity is trapped in a region whose boundary eventually shrinks to zero size. This means that all the matter in the star will be compressed into a region of zero volume, so the density of matter and the curvature of spacetime become infinite. In other words, one has a singularity contained within a region of spacetime known as a black hole. At first sight, Penrose's result didn't have anything to say about the question of whether there was a Big Bang singularity in the past. However, at the time that Penrose produced his theorem, I was a research student desperately looking for a problem with which to complete my PhD thesis. I realized that if one reversed the direction of time in Penrose's theorem, so that the collapse became an expansion, the conditions of his theorem would still hold, provided the universe were roughly like a Friedman model on large scales at the present time. Penrose's theorem had shown that any collapsing star must end in a singularity. The time-reversed argument showed that any Friedman-like expanding universe must have begun with a singularity. For technical reasons, Penrose's theorem required that the universe be infinite in space. So I could use it to prove that there should be a singularity, only if the universe was expanding fast enough to avoid collapsing again, because only that Friedman model was infinite in space. During the next few years I developed new mathematical techniques to remove this, another, technical conditions from the theorems which proved that singularities must occur. The final result was a joint paper by Penrose and myself in 1970, which proved that there must have been a Big Bang singularity, provided only that general relativity is correct, and that the universe contains as much matter as we observe. There was a lot of opposition to our work, partly from the Russians, who followed the party line laid down by Lifshitz and Koladnikov, and partly from people who felt that the whole idea of singularities was repugnant and spoiled the beauty of Einstein's theory. However, one cannot really argue with the mathematical theorem. So it is now generally accepted that the universe must have a beginning. That is all for this lecture.